All right, hey everybody. No funny business on this video, no jokes, no music, no messing around at all, because we're just going to quickly go through section 2.6, which is going to be on conditional statements and their converses. I know you're excited. Yes, I know you're excited. So originally, guys, I told you guys during Wednesday's class that I wasn't planning on doing sections 2.6 and 2.7. The reason why I didn't want to really dive into it is because if we were to do everything in that section, and every kind of expectation that they have out of you, it would probably take a solid 4 classes to do that. Now, as you know, we're only meeting 3 times a week. So 4 days of classes on this? No, that's completely unreasonable. You don't need to know absolutely everything in these 2 sections. So what I'm going to do, instead of spending 4 days going through and making sure we kind of understand these 8 objectives the book wants you to get here, I'm going to focus on just 1 day for section 2.6 and 1 day for section 2.7. Make it kind of quick, okay? Remember, some of the sections we're doing this year, we spend 1 day on. Other ones we spend 2 days on. It'd be nice if we can spend 2 days on every section, because I think you get it better, and I think you feel more confident and less stressed. But the unfortunate thing is, we got ourselves backs up against the wall. We got to keep turning the page, right? And turning the page we'll keep going, okay? So instead of turning the page, doesn't necessarily mean skipping sections. So we're turning the page 2.2.6 because I still want to go over it, because I think it's just going to make things make more sense once we get into chapter 3. And that's just nicer when things make more sense. So even though this stuff isn't critical to know for other classes, it's going to make the geometry in sections 3 and beyond sort of flow, I think, a little bit better and a little more beautifully. And I think you'll hopefully get that stuff that you need to know that you will do in other courses and other standardized tests and other stuff that you want to feel prepared for, right? Because you did geometry this year. All right, so what we have today is we have an abbreviated lesson on section 2.6. Okay, so that has to do with conditional statements and converses. No speeding up at all. I'm not going to speed up this video at all either. You have to speed it up on yourself, okay? Hit that button on YouTube, right bottom right, hit playback speed, just do it twice speed, and then you're going to get done with this. Okay, conditional statements and its converses. Your homework will not be from the textbook. Your homework is this. Please don't start it yet. Let's go through the lesson together before we actually start it. So your homework is this, where you're writing conditional statements and their converses, and you're saying whether or not they're true or not. So what you need to remind yourselves is, well, one, what is a conditional statement? We have gone over that this year, what a conditional statement is, and there's some vocabulary related conditional statements like hypothesis and conclusion that you might be familiar with. And right, we see if-thens, listen, and whatnot. And then you also need to, second thing, know what a converse is. That's what this lesson is. I'm going to show you what a converse is, and then I'm going to explain to you what makes a converse true, right? How can you tell if a converse is true or not? Or how can you tell a conditional statement is true or not? We kind of done that, but we're going to review that here. Last thing in this is that we're going to talk about something called a biconditional statement. Oh boy, let's buckle up. Let's get going, okay? So please wait on this until you've watched the video and taken notes. And then this is what you're doing for homework, is filling out this sheet right here. I'll probably film a different video going through the examples for you, so you can launch into it after you see the examples. And if you notice here, this is just from the school district right here. So this might look familiar to what you're doing in middle school. Those binders and what do you have? The little workbooks, remember those? Okay. Anyways. All right, a little bit more introduction here before I go to your first note. We have at least 3 notes I need you to take down, basically 4 things I want to cover. So anyways, this section here, just want to give you a heads up of what we're doing, because eventually we'll have a short section on 2.7, and then that's on Monday. That'll be another thing. So some of this stuff mentioned here we're going to cover today. Other stuff we'll mention on Monday's video. So just sort of the objectives of this section, the reason why I didn't think it was that important is we're not really talking about fundamental things about shapes. We're talking about the academic language that we use to talk about shapes and kind of the structure and reasoning behind it. So I know we've done a lot with reasoning this year. I felt like we didn't need to do this, but no, I think it'll just be a little bit more calming if we go through those stuff together. Okay, so we got to recognize the hypothesis and conclusion of a conditional. I've already taught you how to do that. We're going to review that. State the conditionals in if-then form. We haven't really practiced that, but any theorem or postulate in your textbook, you can rewrite it as an if-then statement. A lot of times, like for instance, vertical angles are congruent. That's a theorem. You can change that to an if-then statement. So the if-then statement for vertical angles are congruent. Right? You notice here, they don't, in the textbook, they didn't say if or then, they just said vertical angles are congruent. Rephrased as an if-then statement, writing in then an if-then form is, right, if 2 angles are vertical angles, right? We notice that in a diagram, then they are congruent. So your book could have written it out that way. but they don't, right? Because vertical angles are congruent. That's self-evident enough to what it means. It means if you have some vertical angles, then you know that they're congruent to one another. State the converse of an if-then statement. All right, well, if-then statements, those are like two parts of an if-then statement, right? We have the if part and got the then part. What might a converse be? How might stuff move around? Understand the meaning of if and only if. We'll do that today. So we're doing 1, 2, 3, 4 today. If and only if, that's something that appears in something called a biconditional statement. So we'll think about that. And then finally on Monday, we'll have hopefully a quicker lesson on some other related statements here. Okay, so you have the converse is a related statement to an if-then statement, and then you have a contrapositive, and then you have an inverse here. So there are 4 statements in total, 3 of which are related to the original statement. We have the original statement's the first one, then the converse is usually the second one that people look at in terms of evaluating the validity of. And then third statement is the converse. Fourth statement is the inverse. All right, and we'll talk about what those are on Monday. You don't have to worry about it today. And finally, we need to understand the relationship between logically equivalent statements. We'll do that on Monday. Don't worry about that today. All right, jumping into it here. Because, guys, I said we're not messing around. Not playing music. I didn't even shower yet today, I don't think. I'm not even I'm not wearing my button downs today. I'm just getting stuff done. Let's do it. It's that day. All right, note number 1. Write this down in your notebooks. Write it down, write it down, write it down. It's easier so that you don't get zoned out during videos like this to be like looking at Mr. Ford. Hey, what's up, Mr. Ford? Keeping you aware here. But also that you're writing down the notes, okay? You're an active learner, right? You're actively doing stuff here. I know there's a lot of information to learn, but writing it down helps prevent you from zoning out here, okay? So note number 1, it says, any theorem or postulate, I've already said this in this video so far, but I want you to write down, any theorem or postulate we're going to learn this year, or we have learned this year, we can write it as something called a conditional statement, okay? Something called a conditional statement. So just to remind you guys of who is, someone I'm calling on the class to see who's going to bring their prior knowledge to it, all right? Bring the prior knowledge to it. We've talked about conditional statements in the past before. Conditional statements. What are conditional statements? Like, what's another word and the thing we call conditional statements? That being an exit ticket early on in the year, I said, what's another name for a conditional statement? Well, it's a conditional statement because a conditional statement is an if-then statement. An if-then statement, okay? So the then part, right, the thing after the then part, that's a condition, a necessary condition that follows from the if part. Okay, follows from the part. We'll talk about that a little bit later. I don't really need you to worry about the whole necessary part, but the idea is it's a condition of what a conditional statement is that if you say, if this thing happens, then this other thing's going to happen. The if statement here is the then statement is a necessary condition that happens when the hypothesis, the if part happens, okay? If this thing's going to happen, then this thing's going to happen. So under the condition, right? Under the condition we have this thing happen, or we know this, under that condition, then we can make a conclusion. We can make a reasoned conclusion that this is also going to happen. That's why this is a conditional statement, because there's one thing it depends on this other condition so that we can conclude that thing is true, right? So that's why theorems are written as if-then statements. Postulates written as if-then statements most of the time. If not, you can rewrite them as if-then statements because one condition being true guarantees the then statement has to be true, and that's what makes a theorem, right? It makes the beauty of finding facts and knowledge really come to life here. All right, so let's practice changing the following statements from if-then form. So in the textbook, any theorem or postulate, you can write it as an if-then statement. So I might ask you to do that at some point in time, okay? This isn't an if-then statement. Vertical angles are congruent, for instance. How do you, right? How do you? I'm looking at you. How do you write that as an if-then statement? I already did that example here, right? So vertical angles congruent, I can rewrite that as, well, vertical angles congruent. What's necessary here to establish what? So if we have congruent angles, then the two angles are vertical. No, that doesn't make sense. Congruent angles don't necessarily have to be vertical. If we have two vertical angles, then the angles are congruent. Yeah, that's it. So these are kind of to think about a little bit for a second. All right, conditional statement here. Believe it or not, this is a conditional statement. One thing kind of establishes another. One of these two things, the way you're going to do this here, right? Doing one of the things is that you got to look for this. One thing that's stated here makes the other true. Or in other words, one of these two facts are all panthers or cats. What are the nouns here? Well, we got panthers, we got cats. So one of these nouns here, if we knew it were true, then that under the condition that that's true, it's going to be sufficient to establish that the other noun has to be true, for instance, here. So all panthers are cats, that's the statement. Equivalently in the if-then form is that if, okay, what's our if here? What's the thing that would, if we knew it were true, would make the other thing true, okay? If you're a cat, then you're a panther. Does that make sense? If you're a cat, then you're a panther. Well, no. If you're a cat, you might be Garfield, right? If you're a cat, you might be Snowball. If you're a cat, you might be a Siamese cat, right? We still call them those? I don't know. So anyways, the idea of this one is here, right, is that being a cat, right, it gets established by the fact that something's a panther, okay? If something is a panther, then we would know it's a cat, right? Because all pats are panthers, or sorry, all panthers are cats, right? All panthers are cats. So all panthers are cats. That's a fact, right? That's a fact. That's a provable theorem, right? Something like that. I don't know if it's a provable theorem, but basically this is it in if-then form. So anyways, right? You can remember conditional statements. What are they called again? What's another word for conditional statements? If-then statements. If-then statements. Okay, so if an animal, right? An animal is a panther, then it is a cat. All right. So it being a panther is sufficient for establishing that it is a cat, right? Because all pats are all panthers are cats, and the fact that it's a cat was a necessary consequence to the fact that the if was that, well, it's a panther. Well, what's necessary to that is that it has to be a cat too. Okay, so check this one out here. Next one, let's take a look at it. The diagonals of a square are congruent. Oh, are they? Oh, are they? We haven't proven that yet, have we? We haven't proven that yet. So let's check it out here. So I have a square. Oh, man, that was ugly. All right, yes, grid paper. I tell you people, get grid paper. It makes it better. So, wow, this is, yes. There we go. That's what I want right here. Okay, we'll do it right here. Sure. No, that's not a what? I said no. I said no tricks here. No tricks or anything. I was like, I'm not messing around today, but I guess I am because I can't actually do this accurately. Let's see here. That's good enough. Looks like a square. All right, folks. So the diagonals of a square are actually congruent. We'll prove this one in chapter 4, my friends. But anyways, the diagonals of a square are congruent, right? So I guess here, what's the if thing that's necessary, right? The fact that do the diagonals of a figure being congruent? Okay, so let's get that here. Do the diagonals of a figure being congruent, is that enough to establish that the figure is a square, right? So if we knew these were congruent, okay, we knew these were congruent, do we know that that's a square? Well, one thing we'll also learn is this, that the diagonals of a rectangle are actually congruent. Check it out here. That's about the same length as that, right? Because I almost drew a rectangle right there. So to change this statement here, the diagonal, so this is a fact, right? A fact. The diagonals of a square are congruent. It's not written as an if-then statement. Remember, theorems are facts in geometry. You're on fact-finding missions. You're figuring out how to find facts. You can't be argued with here. We're going to prove this diagonals of squares are congruent. But let's try to figure out how we write this as an if-then statement, because if we knew something's true, then we can conclude something else, right? That's how we can string together arguments, write more proofs in the future, okay? So this here, congruent to that thing, is if we have congruent diagonals, then we know the figure is a square? No, that's not true, okay? Because these diagonals are congruent. It doesn't establish a square. So here, the diagonals of a square are congruent. So what we need to say is here, if, okay, I think like the way to look at it here is that if the diagonals of a square, well, if we have a square, then, right, the diagonals, we would know the diagonals are congruent, right? Because squares are also, they're rectangles as well. So if we have a square, so there, that's it here. If it is a square, then oops, sorry, then the diagonals are congruent. And that's that, right? That's that. Diagonals of square congruent, if then form. So it's like, okay, if we got a square, then the diagonals are congruent, right? Wait, if we know we're working with the square right now, what's a conclusion we can make? Oh, diagonals are congruent. Move on to the next thing we're trying to prove. All right. Anyways, we've already done 2 examples. Let's just do this one quickly. The sum of 2 odd integers is even. Okay. So that's a fact here. We add 2 odd integers, we're going to get an even number. That's a provable fact. You can prove that later in your high school experience. We have here. Okay. So if we have, right, 2 odd integers. Okay. If we have 2 odd integers, then the sum is even, right? You just got to kind of logic through that. I'll just do that one really quickly because what depends on what, right, is it's not if we have an even sum, right? That doesn't establish that the 2 things that got added were odd, right? If we have odd numbers, then we know the answer is going to be even, okay? So if you got to think about what is necessary to what. It's necessary. A necessary consequence of having odd numbers is that their sum is going to be even. But a necessary consequence of having even sums isn't that the 2 things added are odd, because it could be 2 evens added together, right? Could be 2 evens added together, okay? So let's check this one out here. If 2 numbers are odd, you liking this so far? Are you liking this? I don't know. I can't tell out there. I can't tell. Then their sum is even. Stay with me. Stay with me. Okay, we're going to do more notes in a second. All right, anyways, I know this gets kind of long here. So if then, right, if then is the setup. We can write any of these facts. Any fact can be rewritten as an if then statement. That's beautiful. It's a beautiful thing. Beautiful thing to learn to know, and it's powerful. Arming you would be able to prove more facts here. So this is more about if then statements. Some things are geometry or math related, some things aren't, and geometry related, and some things are algebra related, and some things just a fact, right? If somebody's awesome is on your team, then you're sure to win. Sure. Steph Curry's on the Lowell basketball team, then they're going to beat Washington. But anyways, one thing I want to show out here is that any if-then statement, okay, follows this, right? We have if, and then we have kind of a yes or no thing. Jane is on our team, yes or no. If, and then we have a yes or no thing. 2 lines intersect. Well, do they intersect or they don't intersect? So we have here, any if-then statement is broken up into something called an if P then Q statement, right? So sometimes it doesn't really matter what's being said here. We just want to look at the structure. Well, what's your P, okay? What's your P here? The thing that P stands for is called the hypothesis, okay? So just reminder on that, the hypothesis is the part after the if, okay, in the if-then statement. So if isn't part of the hypothesis, but Jane is on our team, that's the hypothesis. 2 lines intersect, that's the hypothesis. X equals 3, that's the hypothesis, not if X equals 3. That's not the hypothesis. I gave you feedback on that earlier this year in an exit ticket, okay? The conclusion is the part after the then statement, okay? The part after the then statement. So it's a statement after the then statement, and these are all statements here, right? We are sure to win, yes or no, right? Yes or no. Exactly one plane contains them, yes or no, right? So it's a statement, okay? I want to make a statement. Exactly one plane contains them. So basically an if-then statement is basically a combination of 2 statements, right? If this one statement were true, then is the conclusion going to be true or not, right? True or not true. Does it have to be true? And therefore be a theorem or a postulate. So anyways, just wanted to show you out here that the letters that they kind of use, like we're talking about an if-then statement, I'm referring to the hypothesis. So I'm referring to P, right? The hypothesis gets abbreviated, okay? The hypothesis gets abbreviated by this letter P, okay? P actually stands for something called proposition, which I won't really get into right here, but this is a hypothesis proposition followed by then a conclusion proposition, and so together they form an if-then proposition, okay? So this is how Euclid wrote. That's why when we looked at Euclid's Wikipedia page about the elements, they listed how many propositions he proved, because he actually called his theorems if-then propositions, basically, right? Propositions here. So if P, then Q. This stands for a P. Remember the single-headed arrow, that means if-then. If this is true, then that's true, okay? If that went over your head, that's okay, but it's just like, this is how I'm going to abbreviate things. You'll probably pick up on that later. All right, notes 2, 3, and then we got finally something to say here. I got a meeting at 2:30 as well, so I'm looking at you. You know who you are. So let's go through the rest of this here. Hopefully get through this a bit quicker here. All right, note number 2, if the part after the if is called the hypothesis, you already said that, of the conditional statement, the part after the then is the conclusion. Hopefully you wrote that down. Again, just don't zone out. I try to keep you entertained, but don't zone out here. And then you have a converse statement. Okay, so we've talked about a whole bunch of if-then statements. Okay, hopefully you've picked up on that, right? Theorems can be written as if-then statements. That's a huge takeaway. But the thing we're going to start caring about here, because if an if-then statement were a theorem, meaning it's always true, you might start to look at some related statements. If this if-then thing, right? If two lines intersect, then exactly one line contains them. Or if x equals 3, then x squared equals 9. What are some questions you think scientists or really thorough people would then ask, right? So this is the proposition that we know is going to be true because it's a theorem or it's proven already, right? Which is if x equals 3, then x squared equals 9. Where's a follow-up question? Where can you go from there to actually study? Well, if x equals 4, then x squared equals 16. That's a good guess, right? It's a good guess. But let's use the numbers here, 3 and 9, and maybe just switch it up a little bit. Switch up that statement. Well, what about this? What if I said if x squared equals 9, then x has to equal 3? That might be something you evaluate. We got to think if that's true or not. I don't know if that's true necessarily here. We'll come back to that later. Okay, anyways, what a converse statement is, okay, a converse statement is the reverse of the original conditional statement. And that's kind of, it's not exactly how it's defined, and that might be confusing later because we're looking at even more statements. But what a scientist, what somebody who's really inspecting things, to kind of be clear here, is if you had a statement that you know is true, if P then Q, and let's say if P then Q, this conditional statement here is referring to if x equals 3, then x squared equals 9, you might be curious about what the converse is. And here's the converse, okay? So this is the original statement is this, okay? And its converse, okay, its converse is if Q, then P. Okay, if Q, then P. I gotta move my dog for a second. Again, I said no tricks today. No editing. This is life. This is life as we live it. My dog's about to freak out. We've met Cody before, I think. Let's go. There you go, Cody. He'll be barking momentarily to this here. Okay. All right, so folks, converse, are you with me? I hope you're with me here. Okay, so the converse is just the reverse of that, right? I'm fast forwarding, like, this isn't that hard, right? That's not too hard. Okay, the converse is the reverse of that. So we got to start, our conclusion becomes the hypothesis. So if x squared equals 9, then x equals 3. That's the converse, okay? That's the converse. So the hypothesis and conclusion switch. And then, like, so if a conditional statement's true, you might be wondering, is its converse true? And is there anything else we can do with that here? So the converse of the statement, if x equals 3, then x squared equals 9, is it true or not? Let's see here. If x squared equals 9, then x has to equal 3. Is that a true statement? Is that a fact? Is there, if we think of a counterexample, if x squared equals 9, so x squared means a number times itself equals 9. What are some numbers times themselves that equals 9? Well, 3 times 3 equals 9. Is there another one? Can you give a counterexample? You got to be thorough. Yeah, -3, right? -3 times -3 is 9. So that converse is actually false. Okay, actually false. So this isn't, sometimes converses are theorems or facts. Okay, so this is not a fact. Okay, sometimes you have true converses and sometimes you have false converses. And that's what you got to work with on the homework tonight here. So let's check it out here. All right, so anyways, this sort of explains in the book what I just explained to you guys here. If you interchange the hypothesis and conclusion, you have a new statement that you might be worth evaluating called the converse statement here, okay? So some true statements have true converses. That's what's said down here. True statement, if the triangle is an equilateral, then it is equiangular. Let's practice this together. I'd write this down. Write the darn converse. Do it here. Let's do it here. Well, how do you write a converse? Well, this is our original hypothesis. So this is our P. And then after the then part, this is our Q. If P, then Q. That's just like how like the logicians they're called. It's originally from Aristotle, actually, is like one of the big guys who put together this logic stuff. Aristotle is another early Greek guy before Euclid. So Euclid modeled a lot of his geometry over Aristotelian kind of logic, the way that he mapped out a logical argument. So anyways, that's part of what you're learning this year. So if a triangle is equilateral, then it is equiangular. If P, then Q. So we just need to reverse that. The true converse is going to be if it is equilateral, then it's, oops, sorry, it should be equiangular, because I got to use this over here, right? I got to use the conclusion, my conclusion. So equiangular, then it is equilateral. Okay, what are we talking about here when we use the words equilateral? And, oh, a triangle. Wait, so if a triangle, oops, I missed this part. That was important too. You got to leave the triangle part here. Ooh, just erase the whole thing. I don't want that. No, don't erase the whole thing. There we go. Okay. Erase this. All right. If a triangle is equiangular, so we have an equiangular triangle, then it is equilateral. Okay. And that statement, my friends, is the converse statement, because it's just reversed here. This Q moved up to our hypothesis now. So our original conclusion is now the hypothesis of the converse statement. If Q, then P. Because we have if a triangle is equiangular, then it's got to be equilateral. And this is a true fact, okay? This is a true fact. I don't think we've proven this one yet. Have we proven this one? No, not exactly. Maybe not. We've kind of drawn it out. But if a triangle is equilateral, right, the only way we can draw a triangle with 3 equal sides, right? 3 sides the same length. It's kind of interesting, right? The only way I can draw this, try it, right? The only way to draw 3 congruent sides here is if our angles are all 60 degrees. That's the only way you're going to get it here, okay? So this statement here, if a triangle is equilateral, then it's equiangular. That's true, right? That's true. And we're going to prove that, actually. We'll prove that the next chapter, right? Something called the isosceles triangle theorem we need to get to. And then the converse is also a true statement here. If we knew we had an equiangular triangle, then we're going to know it's equilateral. And that's something that's going to deal with the converse of the isosceles triangle theorem. Remember, equilateral triangles are also isosceles triangles, but isosceles triangles are not necessarily equilateral triangles. Anyways, oof, man, words, crazy stuff here. All right, so we'll get to that. This will be a true, we'll actually cover both of those in chapter 3, so don't worry about those right now, but take it, just accept it. We have a true statement, we have a true converse. You might already be aware of those facts, but you've observed them in the homework of the day. All right, some true statements have false converses. If a figure is in a triangle, figure is a triangle, then it is a polygon, okay? Let's get some practice, friends. I think you know what to do. Let's do if P, then Q, okay? This is our P. A figure is a triangle, then it is a polygon, okay? So we need to write if Q, then P, right? That's the converse. And it's going to end up being false here. They're already giving us to us that it's false. So our Q was, it was a polygon. So if a figure, okay, a figure thing isn't really necessarily that part of the hypothesis. So if a figure is a polygon, so that the if a figure thing doesn't need to move. If a figure is a polygon, then it is a triangle. And that, of course, my friends, definitely false, right? Definitely false, because a figure, if it's a polygon, it could be a hexagon, could be an octagon, could be a decagon. So you have some counterexamples that would disprove that this if-then statement has to be true. So it's only sometimes true. It's only true when you're talking about triangles, right? If it's a polygon, then it's a triangle. Well, it could be a triangle, but it doesn't have to be. So the if-then statement's false. And if it's an always, sometimes, never problem, if a figure is a polygon, then it is sometimes a triangle. That's what's kind of tough about the always, sometimes, nevers, is that if it's a false if-then, it could sometimes be sometimes and sometimes be never. Anyways, we'll practice those more here. Note number 3, when a conditional statement and its converse are both true, people might combine them into only one statement using the words if and only if. Okay, so we've already talked about the conditional statements. And what happens, guys? What's the word for if you reverse the hypothesis and the conclusion? That's called the what statement? The converse statement. Called the converse statement. Okay, so if a conditional statement is true, a converse is also true. So we're talking about up here, that was this case right here, okay? This case right here, both the statement said true statement and says true converse. They're both true. We can combine both of these, right? Combine, because they're both true, right? We can combine them. So I'll write that combine, and we're going to do that down here, okay? We're going to use that using this phrase, if and only if. So you guessed it, this is how we're going to probably change this to a combined statement that tells us basically two facts, two if-then statements that are stated in only one sentence here. Okay, so check it out. A triangle is equilateral if and only if it is equal angular. Okay, it is equal angular. Okay, so know this. This is a way we can say two things at once, right? With one sentence right here. A triangle is equilateral if and only if it is equal angular, okay? This means that a triangle is equilateral if it is equal angular. So check it out here. We have this if thing that's hanging out in the middle. So you're saying a triangle is equilateral if it is equal angular. Look, if it is equal angular. And because we have the only if afterwards, a triangle is equilateral only if it is equal angular. Only if it is equal angular. Okay, so only if it's equal angular is enough to establish that the triangle is also equilateral. So only if that triangle is equal angular will it be equilateral. That's how you can think of only if right here. So the only if appears kind of in the middle of this here, but it's saying only if it is equiangular, then we can establish that the triangle is equilateral. You can think about that as what only if means here, okay? So the if part says, oops, that's the other way around. So only if it's equal to angle, okay, I sort of explained that wrong, but it doesn't really matter. That's part of the reason why I don't want to go into this section too much. Okay, so only if, okay, only if means that as a consequence, okay? So it's the other way around, actually. Sorry, guys. This is why I don't want to spend too much time on this section here. A triangle is equilateral only if a consequence of that is that it's equiangular, okay? So if we know something is equilateral, right, then we're going to get from that, we're going to get the fact that it's equiangular. So knowing something's equilateral, what follows from it, it's equiangular, that's what only if means, okay? That's what only if means. Here, when it just says if right here, guys, this is all very confusing, a bit confusing right here. When it says if right here, okay, what if means is, if you don't see the only in front of it, it means that if this is true, right, if it is equiangular, then it is also equilateral. Okay, it's also equilateral. So notice here the arrows are doing different things. Okay, that's kind of confusing. That's why we're not going to spend that much time in this section. I'm not going to have you do problems out of the book. But anyways, I want you to be aware because if and only if, you got to remember, just if and only if, that tells me two statements. What are the two statements? Well, it means if a triangle is equilateral, then it is equiangular, and also communicates to me that if we have a triangle that's equiangular, then we would know that it's equilateral as well. Okay, so this is sort of more writing about this to sort of lay this down. One thing I've been telling you guys all year, check this out. One thing I've been telling you guys all year is that all the definitions you have learned so far could be stated as if and only if statements, right? If and only if statements. So, right, here's a definition here. Perpendicular lines are two lines that form right angles, tells us two things. And it tells us this, right? Tells us if the two lines are perpendicular, then the lines form right angles. And also tells us if two lines form right angles, then the lines are perpendicular. So that's why all year I've been using this double-headed arrow, not just the single-headed arrows, to show us what if and only if means, right? Because if we knew, for instance, that, let's see here, line AB is perpendicular to, or segment AB is perpendicular to segment BD. What would that tell us? What would that tell us? So segment AB is perpendicular to segment BD if and only if angle ABD is a right angle. Okay, is a right angle. Okay, so any definition, right? The fact that we knew that an angle is a right angle, for instance, that's enough to establish that the lines have to be parallel. If we know that lines are parallel, that's enough to establish that the angles are right angles here. So remember, this is actually something called the biconditional symbol, okay? And it stands for if and only if. So break that up in two sentences here. Segment AB is perpendicular to segment BD if angle ABD is a right angle, right? If angle ABD is a right angle, then that's enough to establish that the line's got to be perpendicular to one another. If AB is perpendicular to BD, to segment BD, only if, so not if, I said if already, okay? Second thing is segment AB is perpendicular to segment BD only if angle ABD ends up being a right angle, right? That's a natural consequence of it here. It's kind of confusing, but The thing is that you need to know is the if and only if thing. Tells you two things, okay? That's called a biconditional statement, and it gets a double-headed arrow. And final thing about this, do you think it? You can explain why it's called biconditional. What do you think that is? Biconditional. What does bi mean? What is conditional statement again? Well, we can explain it because this is basically bi, right? Bi means two, and a biconditional statement is a way to write two conditional statements or two true conditional statements as one, right? Writing two as one. So it's a biconditional statement, meaning singular. It's only one statement, but it's telling us what two true conditional statements are. A biconditional statement here. Okie dokie, that's that. I'm sorry to the person I'm meeting with at 2:30. I'm a few minutes behind. It says here your homework this weekend is to practice doing this stuff, writing conditional statements in if-then form, writing their Converse statements, determining whether or not the statements are true. You'll practice this. I might film another video of this. This will be on a Google Doc. It shouldn't take too long. The long part was watching this lecture and taking notes. Hopefully you did it. Maybe you watched them fast forward. Saves yourself some time. But this is what you're looking at for practice. You're going to practice this one. Again, I just want to get done with 2.6. Want to get done with 2.7 so that we're setting a good stage for chapter 3. And yes, a lot of people have already told me chapter 2 has been better than chapter 1. I agree. Chapter 3 is better than chapter 2, so we're almost there. And that makes me so happy to get to a place where we can just start cranking away and stuff and really practicing it and really seeing how everything connects. That's really the exciting thing. Okay, so what you have in front of us here, anyone who goes to the mall likes to shop. Well, if somebody goes to the mall, then they like to shop, or if they like to shop, then they go to the mall. I don't know. It makes sense there. You can decide. So write the conditional statements. Hopefully you get it right. Say whether it's true, and then write the converse of that, right? Remember, conditional statement, if then. I don't know. I think you guys got this. You guys got this. Have a great weekend. Happy Halloween. I hope you didn't watch this Halloween night being like, oh, this stinks. Take care, guys. I will see you later. Bye. Hey, 36 minutes. Well,